So, diffusion is a very short-ranged force. In the lungs, the air comes into little spherical sacs called alveoli. The oxygen comes in here and then diffuses about 10 micrometers through a very thin membrane into the blood vessels by the side. They can't be any thicker because that's about the distance oxygen can diffuse in a reasonable amount of time. In air it can go much further, but bear in mind water is 1,000 times denser, so the diffusion rate distance is 1,000 times smaller. So instead of a few centimeters, a few microns is about right. Then it's carried down big veins, but normal veins are too large to actually allow enough oxygen to diffuse into cells. So these then split up into incredibly fine veins called capillaries, after the Latin word for hair. These are only a few microns, so maybe 5 microns wide. And from each of these, the oxygen can diffuse into and out of the cell nearby. So you need a vast number of these capillaries. It's about 10 to the 10 in the human body all up, which run close to every cell in the body, allowing the oxygen to diffuse in and out. An incredibly complicated procedure. Is this a limiting factor? Well, in a way it is. The human body, especially when exercising, needs about 10 to the 20 oxygen molecules per second, which have to diffuse from these little air sacs into the bloodstream. And to do that, we need a surface area of around 10 square meters with this very thin membrane. In fact, the human body has about 80 square meters of lung surface area in a healthy person. But how can you pack 80 square meters of surface area into a human who's only like 2 meters tall? The surface area of the outside of the human skin is only a couple of square meters if we're lucky, and yet we've got 80 square meters of surface area to diffuse. And you need that much. This larger amount is to allow some margin of safety so you can exercise and run around and so on. Without that, we wouldn't get enough oxygen to power our muscles. Well, the way we get it is the square cube law. Each of these little spheres, the alveoli, is about 100 micrometers across, which means their surface area is about 4 pi r squared, which comes out as about 10 to the minus 7 meters squared. But we need more than 10 to the 8 of them, but each has a volume of only 4/3 pi r cubed, which is about 4 by 10 to the minus 12 meters cubed. So multiply that by 10 to the 8, the number we need to get you 10 square meters, so that's still a pretty small volume. So this is an example of the square cube law in action by having vast numbers of small alveoli rather than a few big ones. As they get smaller, the surface area goes down as r squared, whereas the volume goes down as r cubed, so you can pack more and more and more of them into a given space. So that's how we get enough oxygen. It's quite a struggle. Really small organisms like bacteria or amoeba are small enough, they're only a few tens of microns across, so enough oxygen can diffuse across their surfaces to keep them going. But when we get to bigger animals like us, or pretty much any normal large animals, this won't work anymore. The only way you can get enough surface area is by having something resembling lungs or gills, some area, some part of the body purpose-built to have with lots of these small alveoli or something similar to give enough surface area and a small enough volume to do it. So is this the limiting factor for human performance? It certainly seems to be quite a struggle to allow diffusion to get enough oxygen into the bloodstream. I'm not sure about this. I actually don't think it is the limit. It's not obvious to me that you couldn't make the alveoli smaller. If you made them, say, 10 microns rather than 100 microns, you could fit a lot more of them into a unit volume with a lot more surface area. Apparently there are some limitations about how small you can make them to stop the walls collapsing inwards, but it's not obvious to me these couldn't be overcome with a bit of evolution. Also, it might be possible to evolve some more active mechanism. At the moment, the body just relies on diffusion, the random thermal motions to get air molecules in and out through these membranes. But many other things are transported through membranes by more active processes, like ions are pumped from one side to the other. So it's not obvious to me that you couldn't have some more active pumping system rather than relying on diffusion to do this. So it's certainly a very great challenge for the human body getting enough oxygen in. We manage it by dint of this very complicated system of almost fractal alveoli, and we couldn't fit a lot more in, but it's not obvious that evolution or some very clever technology couldn't actually improve on this and get more oxygen in. Of course, the way internal combustion engines get their huge amount of power is they spray very tiny droplets of fuel into a cylinder full of air. So the tiny droplets have a very large surface area and can therefore burn really quickly. And that's why you can get a lot more power out of an internal combustion engine than you can from the same region of a human body. So there are other approaches body could in principle take to get this very large amount of oxygen in contact with what it's combusting.